Okay, we're looking at rational functions. So first we're going to look at different types of discontinuities, which are vertical asymptotes and holes. And then we're going to look at horizontal asymptotes, which are our end behaviors. Okay. So what is a rational function? And a rational function is just two polynomials that are being divided by each other. So p of x over q of x. So examples like g of x is equal to x squared plus 2x over x plus 1. Okay. What is a ratio? Yeah, these are just fractional. They're really just fractional equations of polynomials. That's it. Okay. So when is a rational function undefined? It's undefined when we're dividing by 0 or when the denominator equals to 0. We've talked a lot about this. So when is a rational function undefined, and how do we graph that? So it's undefined when you have a vertical asymptote, and we graph that by drawing a vertical dotted line. And this is if we factor and the factors don't cancel out. If they cancel, we get something called a hole. Okay, so there are two types of discontinuities. So when our function is equal to 0 on the bottom, and they are vertical asymptotes, and holes. So we're going to look at vertical asymptotes first. And then we're just going to do like a little sketch of where it would be. So looking at A, when is x equal to 0? Or when is the denominator equal to 0? We'll take our denominator, x plus 2 is equal to 0, subtract 2. We get x is equal to negative 2. So I have a vertical asymptote at x is equal to negative 2. We would draw it like this. At 1, 2, there is a vertical asymptote. And that is it for that one. Okay, next one. Go ahead and factor what makes our denominator equal to 0. So we're going to take our denominator here and we're going to set it equal to 0. So zero product property tells me 3x plus 2 is equal to 0. And also we're going to use x minus 1 is equal to 0. Subtract 2. We get 3x is equal to negative 2. Then divide. So x is equal to negative 2/3. On the other factor, let's go ahead and add 1. We get x is equal to 1. So we have vertical asymptotes at x is equal to negative 2/3 and at x is equal to 1. Okay, so at 1, I would have a vertical asymptote, and at negative 2/3, I would have a vertical asymptote. It's okay to have more than one vertical asymptote. It'll just create more sections of graph for us. All right. So if there's a second type of discontinuity besides vertical asymptotes, so vertical asymptotes are just a break in our graph, and so there's another kind, and these are called holes. So let's look how this works. So our second type, these are holes. Okay, we're gonna factor the bottom. So I'm gonna factor the bottom of the equation, giving me at and the top. Let's factor the top and the bottom. I have a difference of squares, so this is x minus 5 times x plus 5. On the bottom, I'm going to greatest common factor, an x, giving me x minus 5. So I know that at x, when the bottom equals 0, I have either a whole or a vertical asymptote. When the factors cancel, like so, when they cancel, we get the vertical asymptote turns into a whole. So at the 0 of a canceled factor, there is a whole. So at x is equal to 5, there's a whole. Okay. With our other factor, at x equals 0, is a vertical asymptote. Okay, so remember, canceled factors give us wholes. Non-canceled factors in the denominator give us vertical asymptotes. This will look something like this. At x equals 0, let's use some kind of pen. We're going to get a vertical asymptote. And at 1, 2, 3, 4, 5, we'll have a whole. In order to find the y value of the whole, we just plug it into the simplified equation. So into x plus 5 over x. So I'm going to do f of 5. Gives me 5 plus 5 over 5, which is 10 over 5, which is 2. So at 5, 2, there is a whole. So I'm going to go to 5, 2 and graph in 1, 2. It's literally just an open circle. Okay? All right, next. Factor this, please. And we get 3x plus 1 times x plus 2 over x plus 2 times x plus 2. I will see that one of my factors is going to cancel, and one of them stays behind. So this one, even though one of our factors cancels, let's just write it out. I think I have a whole at x equals -2, and I have a vertical asymptote at x equals -2. Since I have a repeat factor, this is the vertical asymptote is going to overpower the whole. So we're still left with the vertical asymptote at x equals -2. Okay? Next, what are the end behaviors of the graph? So end behaviors of the graph are basically what happens with our horizontal asymptote. The horizontal asymptote is weird because it's not really an asymptote, it's just a guideline. Okay, so it's a guideline. In fact, sometimes our graph crosses over the horizontal asymptote, and that is okay. Right? So the first one, what we do for vertical or horizontal asymptotes is we just look at the degrees of the top equation and the degrees of the bottom equation. So for this first one, we have the degree of the top. Oh, that's too big. Degree of top is equal to 2, and the degree of the bottom is equal to 3. So we are bigger on top. Sorry, bigger on bottom. Bigger on bottom. So 0. We call this BOBO. Bigger on bottom, 0. Okay, so this means that the horizontal asymptote is equal, it approaches 0, is y is equal to 0. Think about this for a second. If I'm going to plug in a really big number, like, let's plug in a really big number like 1,000. 1,000 squared divided by 1,000 cubed. Who's going to win out? Well, the bottom is. Eventually, we're just going to get really, 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 really close to 0 the bigger the x gets. Okay. Next one. Who's bigger, the top or the bottom? Well, both degrees are the same. The degree of the top is equal to the degree on the bottom. So we call this EATS DC. Exponents, it stands for exponents, are equal. Are the same. Are the same. So we divide the coefficients. Okay, so of the leading term. Leading terms. All right, so looking at my polynomial at the top, my leading term is 3x squared, and the bottom is x squared. What are the coefficients? Well, they're going to be 3 and 1. So our horizontal asymptote is going to be at y is equal to 3 over 1, which is 3. Last situation is when the degree of the top is bigger than the degree of the bottom. We call this bottom. Bigger, which stands for bigger on top. So we have none. So no horizontal asymptote. We likely have a slant asymptote. So in this case, we actually have to divide the functions to figure out what our asymptote is going to be, like long division style. So we go like this. X cubed plus 2x divided by x squared plus 1. Okay, so we get x times x squared gives us x cubed plus x. Subtract, give me 0, and x plus x. And then I can't divide any further, so this is my remainder. We don't care about the remainder in this case because it's so small once the numbers get really big. So my asymptote is at y is equal to x. Okay. All right. We are going to state the discontinuities, the domain, the range, and the end behaviors for part A, and then we're going to say part B for class. Okay, so this one, first we want to figure out our discontinuities, so let's factor the top. X minus 1, times x plus 2 over, x minus 3 times x plus 2. And we look for factors that cancel. So I see these factors cancel. So I'm going to have a whole at the 0 of that factor. So at x is equal to -2. I need to write it as an ordered pair. So I'm going to put -2 comma something. What we do is we plug in -2 into our simplified equation, which would be x minus 1 over x minus 3. So I get negative 2 minus 1 over negative 2 minus 3, giving us negative 3 over negative 5, giving us 3/5 for my coordinating y value. Next, we look at the vertical asymptotes. So the remaining factors that didn't cancel, I have a vertical asymptote at, so I have a vertical asymptote at x is equal to 3. Okay. Then next, we're going to look at the domain and the range. So we already know from before that x can't equal anything that gives us 0 at the bottom. So with the whole, even before we cancel, we have to find the domain. So we have to use all the factors before we cancel. So the domain is x cannot equal negative 2 or 3. Okay, just like our vertical asymptotes and our whole. So these give us our domain. Okay, and then our horizontal asymptote is decided by the degrees of the top and the bottom. And we're going to look at the original at the leading terms. And the degrees of the top are equal. So this would be eats DC. Okay, we have an eats DC situation. They're equal. So what do? We divide the coefficients. So we get y is equal to 1 over 1 because our coefficient is 1 and 1. Okay, so y cannot equal 1. So this is going to look to set up our graph. This is also we can set up our graph. At y is equal to 1, I'm going to have a horizontal asymptote, which remember is just kind of a guideline. And then at 3, x equals 3, I will have a true asymptote. And then at negative 2 comma 3/5, I will have a whole. Somewhere like there. All right. So that's what this graph kind of looks like. And the range of the graph is y cannot equal 1. Oops. Because of our horizontal asymptote. Though you have to check the graph and make sure that this is true, because sometimes the graph does cross the horizontal asymptote. All right, sorry for the long video. That's it for today.